Right now, kilometers beneath your feet, autonomous robots are fighting crushing pressure and lethal heat to extract the raw materials that power the modern world. The lithosphere does not offer its resources freely. It offers them in absolute darkness, extreme temperature, and structural instability that have killed miners across every civilization that ever sent human beings underground. For 4,000 years, humanity has been descending into the earth, deepening the hole, pushing further into a geological environment that has no interest in human survival. From the Neolithic flint miners of Grimes graves who clawed through chalk with deer antler picks, to the hydraulic shield machines that bore through water-saturated ground in complete safety, the engineering of underground survival has been the most dangerous and most necessary engineering in human history. Every advance in civilization rests on raw materials extracted from the Earth's crust. How do you cut rock, keep the roof above you, manage your floodwater flow, and survive the temperature of life? In this documentary, we trace 4,000 years from Antler and fire, plasma drilling, and how did humanity go from hand-dug tunnels propped with
from the
rotting
surface
timber
down to 4
AI-guided
kilometers,
drilling
reaching the
machines
Mponing
operating in
mine,
underground
the
flood
temperature
zones?
gradient
The gap
increases
between a
rapidly.
Neolithic
Seismic
miner
activity
crawling
detected
through a
on
chalk
level
shaft with a
4.
deer antler pick
Rerouting
and a
autonomous vehicles now.
2026 autonomous
Copy
boring
that.
machine
Adjusting
navigating a
ventilation
seismically
systems.
active deep gold mine is not a spectacle. It is a complete reimagining of what it means to extract resources from the earth. Underground engineering is the oldest and most dangerous branch of engineering in human history. Every civilization that built anything was built from materials that someone had to go underground to find. The history of underground engineering is therefore the history of civilization's physical foundation. The price paid was enormous: cave collapse, flooding, gas explosion, heat stroke, silicosis. Each catastrophe taught the engineers who followed what the rock would not forgive. In this documentary, we trace that learning from the first Neolithic shafts to the deepest mines on Earth, and show how the engineering of underground survival became one of the most sophisticated technical disciplines of the modern age. Civilization is built of raw materials extracted from the most hostile environment on the planet. Every metal, every fossil fuel, every rare earth element that powers the modern world
deep
was
mining
taken
requires
from the Earth's
enormous
crust by
energy
engineers willing
expenditure,
to go
a
deeper,
significant
cut
increase
harder,
from the moderate
and stay
energy
longer
needed.
in an environment that kills without warning. The first miners were Neolithic people who noticed that certain stones made better tools and began digging to find more. They had no engineering theory, only experience, courage, and the accumulated wisdom of everyone who had gone underground before them and come back. 4,000 years later, the mines of 2026 descend over 4 kilometers into the earth, into rock hot enough to cause heat stroke in minutes, under pressures that cause surrounding stone to explode spontaneously. The engineering required to operate in those conditions is among the most demanding ever applied. In this documentary, we trace that 4,000-year timeline from the first
Look at
wound
this
in the
marking
Earth's
on the
surface
chalk wall.
to the deepest engineered access point ever created, and reveal
Yes,
how
it
humanity
looks
learned
like a
to dominate
schematic.
the lithosphere. The first underground engineers were not engineers. They were tool makers who had run out of surface flint. Flint, the dense, fracture-predictable
Following the
silica
seam
rock
here,
that
it
Neolithic
seems to
people
dip
shaped into cutting
slightly
tools, arrow
just
points,
past this
and
cluster.
scrapers outcrops at the surface in limited quantities. When surface deposits were exhausted, the people who depended on flint tools for survival had a choice: move to find new outcrops or dig.
This visualization shows chalk-bearing capacity versus gallery span. When the critical span is reached, the roof inevitably
are
fails.
among the best preserved examples of early underground engineering in the world. The miners excavated earth in soft rock, using antler picks and bone shovels, descending up to 12 meters to reach the high-quality flint seam below. From the base of each shaft, they drove horizontal galleries in multiple directions, following the flint seam by steel and torch power. No structural engineering theory, no ground support calculation. The galleries were driven until the roof began to show signs of instability, and then abandoned the miners, retreating to the shaft and starting a new gallery in a different direction. The physics they were managing empirically, the relationship between gallery span, roof thickness, and chalk-bearing capacity, is the same physics that structural engineers calculate formally today. They got it right often enough to keep moving. They got it wrong often enough to lead to collapse and break. Every collapsed gallery, the archaeological record of an engineering failure mode that the miners accepted as the cost of access to the material they needed. The Romans transformed mining from a subsistence activity into an industrial activity. Their gold and silver mines in Hispania, particularly the massive mines of Western Spain, operated at a scale that dwarfs anything achieved before the Industrial Revolution. The Romans used hydraulic mining on a vast scale, directing enormous volumes of water through aqueducts to erode entire hillsides and expose ore deposits, a technique called hushing that effectively weaponized fluid mechanics against the landscape. Underground,
4,000 years of underground engineering began with one
lintels installed in a pattern that transferred roof loads to the solid rock floors between galleries. They used ventilation shafts to move air through working areas. They used water wheels in series to lift groundwater from flooded lower levels. The engineering was empirical, but systematic accumulated knowledge coded in practice rather than mathematics, transmitted through the mining communities that supplied the empire's appetite for metal. Medieval miners inherited the Roman engineering toolkit and pushed it further deeper shafts, longer galleries, more systematic.
Faster, it's rising too fast!
Until they encountered a problem.
As the
that
mine
Roman
descends
engineering
below
had
the
not
water
solved,
table,
and
the
that
head
would
of
define
water
the
pressing
limits of
inward
underground
increases.
engineering for 1,000 years.
Human-powered pumping
Water.
cannot keep
As
pace.
mines deepen below the local water table, groundwater flooded the workings faster than it could be removed by human or animal power. The deeper the mine, the greater the head of water, pressing in through every permeable rock seam. Medieval and early modern miners across Europe spent enormous effort to drain depths, to intersect the flooded workings and drain them by gravity. Horse-powered steam pumps lifting water in buckets from level to level. Ventilation systems that attempted to manage the damp air that accompanied the water. None of it was adequate for heat pumps. The bottleneck was energy. The mine required more power than any pre-industrial prime mover could supply at the required scale. Thomas Savery's atmospheric steam 1,798 and Thomas Newcomen's improved design 1,712 were developed specifically to solve this problem.
Brunel's shield provides continuous support as it advances hydraulically, allowing for safe excavation and the
To think we are walking
designed to
beneath
convert the
Thames
chemical
right
energy
now.
of coal into the
It is
mechanical
quite
energy
astonishing.
required to lift water
Mr. Brunel
from
has
flooded
outdone
mine shafts.
himself.
James Watt's
my
separate
knee!
condenser
I got
of
the bends!
1,769 made steam engines dramatically
We need a medic!
more fuel
Get the chamber ready, quickly!
richer coal seam that could now be economically worked, provided the fuel to power the industrial revolution that the mining industry itself was enabling. The timber support systems of the early modern mines were simultaneously technology and a limiting factor of underground construction. Timber props and frames could support excavations in moderately competent rock. In waterlogged, unstable ground, the London clay, the
Modern
saturated
Earth pressure
alluvial
balance
deposits beneath
TBMs
major
maintain
rivers timber
continuous
provided
pressure balance
inadequate
by using
support
the
against the
excavated
plastic
material
deformation
itself
of
as face
water-saturated
support.
soil.
We
Mark
did
Isenberg
it!
Brunel's tunneling shield, patented in 1818 and used to drive the Thames tunnel between 1,825 and 1,843, was the engineering breakthrough that made tunneling through unstable ground possible. The shield was a cast iron frame that supported the face of the excavation, while miners worked within it. As each section of tunnel lining was installed behind the shield was advanced hydraulically into new ground. The principle maintaining continuous support of the excavation phase, while simultaneously installing permanent lining, is the basis of every modern tunnel boring machine. The gold mines of the Witwatersrand Reef in South Africa presented underground miners with a problem that no previous mining had encountered at industrial scale: depth. The gold-bearing reef
removes
dips
rock.
steeply into
Stress
the earth
redistributes
at an
into
angle that
surrounding
requires
rock.
following it
At
to
critical
ever greater
stress
depths to
concentration,
maintain production.
rock fails
By the
explosively.
mid-20th century, South African gold mines were operating at depths of 2 to 3 kilometers. By the late 20th century, the deepest mines on Earth, the Mponeng and Tautona mines,
Automated alert.
south of Johannesburg,
Seismic
were
activity critical.
approaching and then
Evacuate
exceeding 4
immediately.
kilometers of depth. At these depths, the physics of the lithosphere becomes actively hostile in ways that shallow mining does not. Rock temperature increases with depth at approximately 25 to 30 degrees Celsius per kilometer. At 4 kilometers, the surrounding rock is at temperatures exceeding 60 degrees Celsius.
At this depth,
And the rock
at this
surfaces
depth,
exposed
the rock
by
surface
mining
temperature
can
creates
reach
an
surface
immense heat
temperatures
load.
of over
The
65
refrigeration
degrees
system
Celsius.
is vital.
Unventilated working environments at these depths would kill an unprotected worker within minutes from heat stroke. Punning operates the largest underground refrigeration system in the world.
We monitor the surrounding rock mass continuously. This geological disturbance affects stress levels.
The refrigeration load required to make Mponeng habitable for human workers is equivalent to the cooling requirement of a small city. At ultra-deep levels, the confining pressure of the surrounding rock creates a phenomenon called rock burst. The spontaneous explosive failure of rock faces exposed by mining as stress concentrations are relieved violently. Rock bursts kill miners without warning. The engineering response combines microseismic monitoring networks that detect stress accumulation before failure, distress blasting that deliberately induces small controlled failures to reduce stress accumulation, and support systems of high elongation rock bolts and mesh that contain the energy of a rock burst, rather than trying to resist it. The transition from manual labor to mechanical drilling at depth was driven by the same physics that made depth lethal. Human beings operating pneumatic drills in high temperature, high humidity environments at depth accumulate heat stress faster than they can work. The mechanization of drilling continuous miners, longwall shearers, raise boring machines, removed human beings from the most
Alert level
dangerous
red.
and
We're showing a
physically
catastrophic
demanding
structural
parts of the
failure in
process,
Sector 6.
while
Stabilize the
simultaneously
pressure
increasing
immediately.
productivity
Reroute
by
power to the
orders of
support
magnitude.
braces.
The underground mine of 2026 is not recognizable as the descendant of Grimes' graves, except in its fundamental purpose. Raw material enters the Earth's crust as geological deposit and leaves it as extracted ore. Everything between those two points has been transformed by digital technology, autonomous systems.
The
and
accuracy of
real-time
autonomous
geological
drilling
intelligence.
exceeds
Digital
what is
twin
achievable
technology,
manually.
The continuous computational modeling of
Mechanical
the mine's
drilling
structural
uses
state
contact
sensor
and
data
compression,
allows
leading to
engineers
wear.
monitor every major
Plasma
geotechnical
drilling
parameter
uses
of
thermal
an
energy
operating
and
mine simultaneously. Stress sensors embedded in the rock report load changes in real time. Microseismic networks detect the acoustic signature of stress accumulation in the rock mass around mine locations, providing warning of potential rock bursts hours or days before they occur.
The pressure readings on
Ground-penetrating radar
sublevel 4
surveys
are
update
stabilizing.
the geological model
I'm increasing the flow rate to the
continuously as
hydrodrill
mining
3 now.
advances, replacing the historical lines of sparse borehole data with dense, continuous geological intelligence. Autonomous haulage systems, fleets of driverless trucks and loaders, operating in underground environments, have been commercially deployed in multiple mines globally. They operate continuously, without shift changes, without fatigue, without exposure to the environmental hazards that constrain human operation. In low oxygen, high temperature environments where human biology cannot survive without extensive life support, autonomous machines operate without constraint. The Komatsu crusher and similar systems navigate underground haul roads using precision GPS-denied positioning systems, LiDAR, and pre-programmed route maps updated in real time from the mine's digital model. Plasma. Drilling the use of high-energy plasma jets to thermally fragment rock rather than mechanically cutting it is moving from laboratory demonstration to operational trial. The technology eliminates the mechanical wear that is the primary maintenance burden of conventional drilling equipment and can penetrate rock chambers at speed conventional. High-energy thermal fragmentation removes the last major limitation of mechanical drilling. The rock
More
hardness
gold
ceiling,
per ton of
beyond
smartphones
which
than per
conventional
ton
builds
of
cannot
gold
operate
ore.
economically. These technologies are converging toward a mining operation that is, at its most advanced, entirely autonomous. A robotic system that descends into the earth, maps the ore body, extracts the material, and returns it to the surface without human intervention. The deep drilling infrastructure of the 20th century mining industry, the shafts, the ventilation
From the
system,
low gravity
the
and
haulage
vacuum of the
networks
moon
represents
to the
an
extreme
enormous
heat and
engineering
pressure
asset
deep
that
within
is
the
being
earth,
repurposed
the
around
engineering
the world.
challenges vary
Its
immensely.
builders never imagined. Abandoned mine owners and deep borehole networks are being evaluated as carbon capture and storage sites, geological formations, capable of sequestering atmospheric CO2 in quantities sufficient to contribute meaningfully to climate. Mitigation. The same understanding of subsurface geology and fluid mechanics that enabled deep mining is being applied to the problem of underground carbon storage. Urban mining, the recovery of valuable metals from
This
streams,
is the tool
rather
that
than
started
virgin ore,
everything.
is transforming the economic
Beside
model
it,
of the mining
a
industry
modern
in
smartphone.
parallel with its technological transformation. A smartphone contains recoverable quantities of gold, silver, copper, palladium, and rare earths. Urban mine streams, waste electronics, industrial slag, tailings from historical mining operations contain metal concentrations that in some cases exceed those of the original ore deposits from which they came. The engineering of urban metal recovery is an emerging
The
discipline
circular
that applies the
depressions in the pale
hydrometallurgical
ground,
and pyrometallurgical
the first
techniques
holes,
of conventional mining
everything
to
began
secondary
here.
material streams. The most radical extension
This
of
is the
underground
tool
engineering
that started
is leaving
everything.
the Earth entirely. The moon's
Beside
surface
it,
contains
a
deposits
modern
of
smartphone.
helium-3, rare earth elements, and water holes. Near-Earth asteroids contain metallic iron-nickel bodies, with platinum group metal concentrations orders of magnitude above any terrestrial ore. The engineering challenges of extracting these resources, operating in vacuum, in microgravity, without the possibility of human intervention, for emergency repairs, are extensions of the same engineering problems that Neolithic miners faced at Grimes' grave. How do you cut rock, remove it from where it is, and get it to where it needs to be? 4,000 years ago, a miner in a chalk desert in Norfolk pointed a deer antler at the wall and started digging toward the materials.
From the low gravity and vacuum of the
Today,
moon to the
engineers are
extreme
designing
heat
robotic
and pressure
systems to do
deep
the
within
same
the
on
Earth,
surface of
the
an
engineering
asteroid
challenges
400 million
vary
kilometers
immensely.
above Earth. The physics of rock fragmentation has not changed. Only the scale of human